Hello friends, so the topic of my lecture is today electromagnetic equation for electric and magnetic field in conducting medium and their solutions. And here is the equation you can remember. This is similar to the wave equation without the conducting term. This will be this and this term will be present, only the extra this term is there. This is the conducting term. So we'll discuss about the attenuation of the electromagnetic wave in the conducting medium, the phase lag between electric and magnetic field. We'll just show the electromagnetic survey in geophysics as well as the magnetotelluric method, very sophisticated technique. So step by step I will just show you every derivation so that you can also practice in home. These are very important topics in application wise in basic physics. So this is the pictorial depiction of the electromagnetic survey and the magnetotelluric method. So we'll first show the electromagnetic wave in conducting medium with no free charge. That means rho is equal to 0. The previous description is same as that. D is proportional to electric field, magnetic flux density proportional to H, and J is equal to, this is the Ohm's law, sigma into electric field. So I'll show that now the four Maxwell's equation. If you don't know or you are finding difficulty, please follow my previous lecture. There I have shown every step-by-step derivation of the Maxwell's four equation and its physical interpretation. So this is first equation is like, this is the Faraday's law, this is the Ampere's Maxwell's law, and we just replace the term B, replace the term J and D. And these two equation, this is the magnetic monopole doesn't exist. It's the famous Gauss law with right hand side free charge equal to 0. We have to take current on both sides to reach to the wave equation as we have done before in non-conducting medium. So taking the current on both sides, and you know from the vector identity this term is like grad dot E and grad square E. And now again grad dot E, this is equal to divergence of E is equal to 0 because free charge, there is no free charge we have assumed. So only this term is prevalent, and now we'll just little bit mathematics, little bit derivation, we can reach to that equation. So only the difference in the equation is that here the conducting term sigma mu and the partial derivative of E, that is present apart from this and this term. So if that term is not present, then it will reach to the familiar wave equation in the non-conducting medium. In the presence of conductor, this term contributes, and I will show you later that this term contributes to the loss in energy, attenuation, in the conducting medium. So similarly, we can reach to the equation for the magnetic field. So it will be a home task for all the students to reach to that equation of that grad square is the electromagnetic equation in conducting medium for magnetic field, that I have shown the steps. So the next, so it's my request to all the students, please solve that electromagnetic equation for the magnetic field in your own hand so that you can have a grasp on it. Either you do on your own hand or by yourself, you will not getting the feel of it. So you do it by your own. I will give the solutions of that wave equation. So in general solution, in my previous lecture also I have shown you the space part and the time part. This is the space part and this is the time part. This is the in general solution, and we have a famous equation. So when we just substitute that electric field, we can reach to the solution. So very easily you can visualize it, because if a grad square means this is a space part, double derivative. So it has double derivative with respect to that r. So we are having term ik dot ik. So ik dot ik will convert to minus k square. Now the second term is partial derivative with respect to time. So sigma mu term is present, and with time it will have I omega minus. So minus minus plus. Similarly, the last term is derivative with respect to second derivative with respect to time. So we'll have I omega into I omega. So minus omega square and minus minus is a plus. So we'll, and right side is this vector, electric field vector. Now we can have for k square is equal to sigma mu omega square plus this term. You can see that wave vector k is itself a complex quantity in a conducting medium, unless in the non-conducting medium. You can easily visualize from the mathematically. So we can write k is equal to some real part plus imaginary part, and we have to do the square of k. So you can see this is the k square and this is also k square. So you can equate this k square term alpha square minus beta square and is equal to mu sigma omega square, and 2 alpha beta is equal to omega sigma mu. So you can see that there are these two equations. So from these two equations we can convert to the this alpha and beta. This alpha physically, what does it mean? Physically beta means it contributes to the attenuation. I will show that. And alpha is contributed to phase factor. So this alpha and beta, this is a conducting medium. With a little bit algebra you can reach to this term. So you are having a square minus b square, so we will have a square plus b square is equal to a square minus b square whole square plus 4ab. So with that you can reach to this. So I again request to all the students, please do some mathematics and algebra to reach from this equation, from these two equation to the solutions of alpha and beta. Okay, you can solve it by your own hand very easily. This is the equation 8. Mathematically I'm just showing. Now we'll move to the skin depth. What is the physically means? So when you are just when you just substituting the solution, what will get? You will get that electric field is equal to e to the power minus, you have substitute e to the power I into k dot r minus omega t. When you replace k is equal to alpha plus I beta, you can reach to that part. So you can see this is the modified space part, e0 into to the power minus beta. This is attenuated. You can see there's a clear attenuation in the exponential term. And physically what it means the wave set up electric current in the medium, and that causes the dissipation of energy. How? In the form of heat. So if there will be a wave that is entering in the conducting medium, there will be an attenuation of the wave, and that is because due to the joule heat loss. So in many interview we can face the question, or physically the meaning of skin depth or the attenuation of attenuation of the wave. So first I will move to non-conducting medium. For non-conducting medium, this term sigma divided by omega epsilon, sigma is very less, so it is 0. So with the equation 8 we can have alpha and beta both are 0. Okay, if alpha and beta both are 0, then there will be no attenuation or absorption. Beta is 0, so no attenuation. So the wave that is entering in the medium, it will have the full amplitude. Next we'll move to the conducting medium. If for a good conducting medium, this term sigma is very greater than omega, the frequency of the wave, and the permittivity. So it will be very greater than when you can realize, and for that alpha and beta will be having that value of root over mu sigma omega by 2. Okay, this we get from equation 8. So you substitute that is very greater than 1. Algebra, you can find this term to be converged in a solution like this. Now what is 1 by beta? 1 by beta measures the depth at which the electromagnetic wave, which is entering in a conducting medium, is damped to 1 by e of its initial amplitude. It is known as the skin depth. So this is the depth from that attenuation. From the attenuate, this is a new amplitude what I am showing, and this will be e0 into to the power minus beta r. Okay, so this is the exponential decay. Now delta, we can have that skin depth proportional to 1 by imaginary part of the wave vector, and that is proportional to the inverse of the root of the frequency, that skin depth. So if there is an increase in the frequency of the signal, then the skin depth will decrease, and it also depends on the conductivity of the medium in a vice versa. So if the conductivity of the medium also increase, the skin depth will decrease. So in more the conducting medium, the more will be the attenuation, that means the more will be the skin depth. In that way you can realize more will be the attenuation and the skin depth will be very less, sorry. So now if we can substitute the solution E and H in the divergence of E is equal to 0 and divergence of H right side is equal to 0 homogeneous equation, you can find this is K dot E0, K dot H0 means it is a transverse wave. Direction of propagation is perpendicular to the electric and magnetic field. This is same as the non-conducting medium. So for conducting medium, non-conducting medium, this equation is same. This transverse wave theory. Now, so I want you to visualize that skin depth part, how the electromagnetic wave converges. So there is a free space, suppose. So I have drawn this for you, only for you. This is only for the understanding purpose, not more than that. So this is a free space means sigma is equal to 0. The wave is entering medium. And now when it enters the conducting medium where the sigma naught is equal to 0, the amplitude of the wave decreases. And this is the full amplitude. This is skin of the surface. Skin means use of the mid conducting medium, the surface of this conducting medium. In that way, it is the nomenclature is justified. At a distance of delta, the amplitude becomes 1 by E of the maximum amplitude. So this depth can be thought of as a skin depth in the conducting medium. Now what we can see, there will be a decrease in the strength of the signal in the conducting medium, but in a free space there is a no attenuation of the wave. Okay, and the maximum amplitude is here E0, and that amplitude becomes E0 by E at some depth delta, so e to the power minus beta delta. From here we can get the same in the previous slide. The skin depth is 1 by beta root over 2 by mu sigma omega. So we can have skin depth is dependent on the various frequencies, various material. For micro frequencies, in a micro frequency for Ag silver, the skin depth is very large, and for Au gold also it vary from metal to metal. So this technique of the skin depth is used in a application purpose, and it reduces the for reducing the material cost of the good conductor. So the vast application is there for the skin depth technique in many application. So this theory you need to know for doing the application purpose. Okay, so you can find it to be a very rich phenomena in physics and any application purpose, and also in geophysics that I am going to show you. Now you can remember there was no phase difference in electric and magnetic field in a non-conducting medium, but there is a phase difference interestingly in conducting medium. So you can find that curl of that common equation. If we insert the E and H solution, you can get, if we insert E is equal to E0 into the power I into K dot R minus omega t. So K cross E will be in the left side I, and the first partial derivative of that with H term will produces minus I omega. As you can imagine, visualize very easily, you can do it by hand. So K cross will be mu sigma omega. Similarly, if we substitute the H equation in there, you can have the same I into K cross H. The space term will be Ik, so I will be left hand side, sigma will be unchanged, sigma E, and there will be a term as a term as sigma and partial derivative of E, that will produce the term of I omega into epsilon. So K cross H will be that term I sigma epsilon omega, and in the right hand side electric field vector. Okay, so from that equation we can find the magnetic field density will be that we replace the K vector as alpha plus I beta. K is a vector here, so this is also a vector as a unit vector in the direction n cap cross electric field vector. Now for any complex number, complex quantity, with this argument and with this absolute value argument, we can write that the absolute term, that means magnitude is root over alpha square plus beta square, and e to the power I into phase means phi. Phi means tan inverse of that imaginary part divided by the real part. Okay, so now for a, you can see that to the this phi becomes pi by 4. That means tan inverse 1. 1 means pi by 4, 45 degree. That is for only for good conductor, these two terms. Specifically, for good conductor, this magnetic field reduces to electric, the magnetic field vector that reduces to this equation. So there will be a phase difference between magnetic field density and electric field in a good conductor, and that phase difference will be 45 degree. And if we just, so just pictorially you can imagine that imaginary vector plane, that is real plane, there is electric field vector in that side, the magnetic field or density or vector will be that side, there will be phi angle, and this is alpha, this is real, this is, and this is a beta. Okay, this is on the real part, real axis, this is on the imaginary axis, the beta is imaginary. You can find there is a phase difference of 45 degree for the good conductor. This angle is almost roughly 45 degree. So for a good conductor, the magnitude, the ratio of the magnitudes for magnetic and electric field will converge to this root 2 alpha divided by omega mu, and this term is that magnitude term. So this term will be 1, and the magnitude term will be that if you replace the value of alpha for a good conductor that I have shown, this comes out to be that this proportional to that root over of the conductivity, inversely proportional to the frequency and the mu permeability. So in general, magnetic field and electric field are not in phase, but mind, for a non-conducting medium, electric and magnetic field are in phase. H lags behind the electric field by angle this phi. I have bold, made it bold to make you realize this factor, tan inverse beta by alpha. And for good conductor, this beta is equal to alpha, so we can have tan inverse 1 means pi by 4, so e to the power I into pi by 4. From there we can get it. This phase lag is 45 degree. So this term, this phase lag, is there for electric and magnetic field. This term is applicable in this electromagnetic survey, which I am showing you in my some application part for geophysics. So, and in general, electromagnetic energy is not equally shared, unlike in the non-conducting medium, because the magnetic field energy is greater than the electric field magnitude. So in that way, the energy is mostly magnetic in a conducting medium, because the magnitude of H is greater than E. Okay. So this is the previously I have shown you that slide in my last lecture. Please follow same thing. Only I have introduced this extra things that is in the magnetotellurics and the EM induction. Pictorially you can visualize that is in presence of conductor. Rest is also same. Already we have discussed it, so no point of wasting time here. Only you can see that in presence of conductor, this application term is there, electromagnetic induction and magnetotellurics, that I'm going to discuss you. Now ground penetrating radar is used in case of the wave equation with a high frequency. Now let's move to the application part. Until now we have discussed only the theory part of and the physics of electromagnetic wave in the conducting medium. That is very much needed prerequisite to know the thing in real field or the geophysics. So this is the conduction term you can get, and this is the displacement term. Okay, so in a practical wise, the for conductivity for rock and soil is very less. This is the range, and for ore body you can see any from standard textbook, 10^3 to 10^5 ohm meter inverse is the unit of resistivity, and inverse is the unit of conductivity. So for ore body this is very high. Suppose our electric dipole oscillates sinusoidally, so you can write this daily means E0 is equal to e to the power I, that is I omega term is there. So daily delta we can write that omega E, and del 2 E del T square omega square E. Okay, so we can write the magnitude ratio of the displacement, this term and this term. For conducting non-conducting medium this term was not present, but for conducting medium this term is present, and this term will be more dominant. If we can see that for magnitude ratio, that this term and this term, if we replace the value of del 2 del T square and del E del T, that partial derivatives, we can find that this magnitude ratio is proportional to the frequency, permittivity, and inversely proportional to the conductivity. Now you can see for highly conducting medium, that you can see that whenever electromagnetic survey we carry out, that is carried out in a low, below 10 power 4 hertz, means almost below 10 kilohertz. This f is low, and for for this low frequency, the magnitude ratio is very less than 1 in good and also in the bad conductor. So magnitude ratio is very 1 means this term is negligible, so we have to consider this term, denominator term, for that. So for electromagnetic survey, we'll take into consideration grad square V is equal to mu sigma del partial derivative of V. And in that way, in that, if we replace that, the electromagnetic signal passes through the ground in a diffusive manner. So we'll having diffusion equation for this first partial derivative, means there will be a loss, there will be diffusion of energy, unlike in the wave case where there is no diffusion. So the above equation in 1D we can write, omitting this term, we can write only this partial derivative, second derivative in 1D, and this term. So heat equation will be there, so there will be loss term like that, e to the power minus, we can write that 1 by delta, means that beta z, imaginary part of wave vector, and this is 1 by delta means that beta z minus omega t. So we are having this diffusion equation for electromagnetic induction or conduction. We can have diffusive equation. Now let's read some quantitative value. The delta is equal to 500 meter, means skin depth, for normal ground, means for low frequency signal, and that sigma value is 10 power minus 3 ohm meter inverse. But in a ore body, where the ore body there's a frequency will be very high, that and root over 2 by mu sigma omega, you can know that. So inverse, the denominator term will be very high, and the conductivity in ore body, the conductivity is also very high. You can see that 10 power 3 10 power 5 range, but with the same frequency, that skin depth will be very low. That means the wave in a ore body diminishes or attenuates very rapidly with the same frequency as in the case of the normal ground. Okay, so there we are also having the diffusion equation. And in non-conducting medium, I again repeat, I am just comparing this conducting and non-conducting medium so that you can have advantage of just remembering everything. You must have some basics of it. Okay, so now I'll move to this application part, electromagnetic induction surveying technique. So how will do electromagnetic induction? Here we use a coil or cable simply as the transmit, which is transmitting a primary alternating coil, and we will be having another coil which is the receiver. It will receive the primary and the secondary signal. Now, if there is no conductor, then the secondary signal will not be induced in a receiver. But if there is a good conductor, although here the conductivity of the rocks on soil I have shown in the previous slide is very much less, so it will not induce any current to it. But if a good conductor is present, it will set up a eddy current. So pictorial, you can see this is primary alternating magnetic field is receiver of both primary signal and the secondary signal. Now if there is a conductor, there will be induced eddy current will be induced. So conducting ore body, this secondary alternating magnetic field will detect in the receiver. So receiver will detect both the primary, P means primary, S means secondary, as a T means transmitter. Okay, so very simply, this is a very I mean, just basics I am going. There will be a lot within that, but I am not going the deep into the survey. Only for your convenience, I am just telling the basics how it has been carried out. Now, if there is a magnetic field in the conductor there, it will experience a phase shift because of the phase difference. The primary and the secondary field in the receiver, there will be phase difference. Theoretically, I have discussed. So you can see that is the phase difference of primary field, and there is the secondary field. So phase difference will be phi, the phase difference in that in a receiver. Okay, and whenever what it induce, actually the electromagnetic induction, it is producing an average value of the electrical conductivity. but its resolution is far better than potential field method. Potential field is gravity, magnetic, that the geophysics method. So because data accuracy is very low in that method, potential field methods, the resolution is just not very much of in a significant sense. Now the EM induction method, it is very useful for airborne surveys. We can have airborne surveys which is carried out with a fixed wing aircraft, but nowadays they are more commonly is helicopter. Actually helicopter adapt things better to the terrain roughness. If the roughness of the terrain is more, then helicopter is more suitable. So EM induction method has been done using the method of electromagnetic wave of conducting medium. Using the theory, EM induction method is generally carried out. Now I will show you another method, sophisticated. That is a magnetotelluric method. It is also one of the application of electromagnetic method in conducting medium. So this is the passive electromagnetic source field. We are not giving any external source, active source. There will be long period and the short period. Okay, long period and short period signal 10 to the power 4 up to 10 to the power 4 second, and there will be also less than 1 second. Okay, so pictorially let me show you. There will be solar wind, so charged particle induced in it, and there will be a telluric current induced, but that electromagnetic field generated or originated, it will fluctuate between that bounce back between ionosphere and the surface of the earth and induce telluric current in the earth. So it is, you can see, it is the passive source of electromagnetic source field. Also thunderstorm also produce that electromagnetic energy that is bouncing back between ionosphere and the surface. It's a source of magnetotelluric energy. Now we can say that for showing that for magnetotelluric method is also carried out for doing conductivity survey of the earth. So in that we can say that we can assume plane electromagnetic wave propagating in a z direction, and let the electric field is along x-axis and the magnetic field y-axis, and wave is propagating in a z direction. So we can write that equation for the magnetic field, the diffusion equation with the conductive term, and from Ampere's equation we can have the derivative of by with respect to z electric field. We can find that, and replacing that we can find ex by by. We can convert this equation with the resistivity can be written as the inverse of the conductivity, and we'll just find this equation for the resistivity, ratio of the electric field by magnetic field square. In the same way you can find electric field in the y direction and magnetic field in the z direction. You can find rho. So this in general, this rho is a tensor quantity, means rho or z. Z means it is the impedance, means the ratio of the electric field and the magnetic field. In magnetotelluric method, our main aim is to compute that tensorial form of z, xx, xy, xa, yx, yy, yz. So in general, it needs a sophisticated computation technique to calculate the value of that impedance method. Now this rho is the apparent resistivity. Very shortly I can say apparent resistivity is different from true resistivity. Apparent resistivity means resistivity obtained using different current and voltage source method, not the true resistivity of the material. So in that sense, for the half space electron, half space earth, that apparent resistivity equal to true resistivity. Now, in general, for magnetotelluric method, in addition to the Bx By component, the vertical component is also recorded for interpretation in 2D structure. And generally, we are having two electric field components and three Ex, Ey, and Hx, Hy, Hz. Three magnetic field components recorded in the magnetotelluric method to prove the conductivity structure of the earth, same as the electromagnetic method. And here you can find this. I should tell you that zxy will be component ex by hy, zyx means uy by hx. Similarly, zxx means ex by hx. Tensorial form. It measures the time variation of electric and magnetic field and produce a time series data. Generally, who are working with the time series data, they can have the experience of the magnetotelluric method. I have told ample times this is a very sophisticated techniques to prove the conductivity structure of the earth and very emerging field. to work or to carry out research work, and it will produce the electromotive conductivity or inversely the resistivity structure of the subsurface. So pictorial, you can see the plane wave is coming onto it, the fluctuating electromagnetic field. It will record a three electric field XY component and magnetic field X, Y and vertical Z component. It is being recorded here. So generally the impedance, this Z omega is complex, and the associated phase is some tan phi, means imaginary part of that Z by real part of that Z. It will produce a phase. So the equations, this is called tensorial equation. Ex is dependent on zxx and zxy. You can find that matrix from ex ey, and this is the matrix zx zxy zyx zyy in a 2D form. So is this phase, it doesn't depend on the resistivity. And earth behaves like we know an ohmic conductor, so there will be J is equal to sigma. That equation is valid here, and which is a purely diffusion process. So conductivity, conductive term addition will produce a diffusion equation, whereas the wave equation is that is the wave equation. There will be in a non-conducting medium, there will be no diffusion. So the main thing will compute that this impedance zxs, these terms are measured in the empty survey. So very short or in a very brief way, I have described that magnetotelluric method as an application of electromagnetic wave in conducting medium. But this is a vast chapter, so in one slide it will not become described. So later in I will of course describe it, if the time permits, in a detailed way, the magnetotelluric survey. So lastly, I can say that this electric and magnetic field, this contain numerous frequency, and that some can be noise and some are geophysical interested. So you need to have a sophisticated data processing technique, and if you are having the experience of power spectrum analysis, filtering, so you can master the art of analyzing that magnetotelluric data in your as your research topic. You will be welcome for doing that. It's a very emerging topic in the data, which will have the theory of electromagnetic method in physics and the application of time series data analysis, which is very emerging and developing at a faster rate. I hope you have enjoyed or understood some of my lectures, and I am again requesting to every one of you, please do the calculations by your own hand to have grip on the subject and to know every phase, amplitude, electric field, magnetic field terms of your on your own. And if you really like my lecture, please turn on the bell notification icon, like it, comment it. I'll be happy to address your all the comments. And this is my channel names, Physics and Geophysics Learning with me, with my name. Okay, thank you everyone.